Yeah, I mean, I thought I wanted to start this one in a fairly traditional way. Always interested in like how, number one, like just how people got to do what they do, and also I think this can often be a nice way to kind of introduce topics and what makes them interesting and appealing. And so maybe kind of quite classically, you studied physics. I mean, first you're, I believe, from Austria, and then you studied physics in Germany. So those are two choices. Why make both of them in that particular way?
Why Germany and why physics? Well, Austria and Germany are kind of a very similar culture. If there wouldn't have been this thing like the Second World War, maybe they would be one country or not. So I guess I originally kind of was born in Salzburg. I actually went to school in Germany. And so kind of I don't really see it as two completely different things. When there's a football match of Germany versus Austria, I would root for Germany, for that matter. Why physics? I guess it was just something that I was kind of used to and good at in school. Originally, I come from a background of artists. Both my parents are artists, and I was kind of in a school that was kind of focusing on art and theater and those kind of things. And so I was kind of the black sheep in working in physics. I liked physics simply because you can kind of think very stubbornly in your strict rules. And that was something I was kind of good at. And so I went into physics, even though I was really interested in the brain. So before I went to physics, I even tried to understand how the mind works, how like consciousness works, and then how a thought is done. And I had a lot of fun doing physics in Munich and Germany. Specifically, that was an exciting time with the Large Hadron Collider. So I did a bachelor thesis looking into gas mixtures at the Atlas detector in the ion chambers for the Large Hadron Collider at CERN, which was kind of fun at the time. However, it is not really affecting your everyday life. And so I tried to go back into the brain a bit, which was a hard task. Like in my master's project, I wanted to do something about intelligence or thoughts or consciousness, which is a difficult endeavor in the sense that there are people who combine physics and the brain or the mind, but it's kind of a tricky territory. Like you can only look into that domain of combining physics and the brain if you have a career that's kind of too big to fail, for that matter. Penrose does something like that, or your previous advisor, Friston or something. They kind of combine physics with thermodynamics, or there are people like looking at quantum consciousness and those kind of things, where it's very tricky that you end up in the kind of woody section of the bookstore and end up being cited by the wrong people. So I couldn't find any advisor that would want to work with me on this kind of esoteric, weird thing that's kind of not even kind of true, strict science like physics is, where there's a kind of ground truth at the end. I found a supervisor that was interested, or at least allowed me to work on artificial neural networks. That was back in 2010, before kind of the boom of AI, to simulate a robot that has curiosity. It wasn't really his area of expertise. He just allowed me to work on it. And I'm glad I didn't follow through and did my master's with him and kept Googling. And on Google, I typed in neurophysics, and voila, it turns out that this is actually a thing. And there was this Max Planck Institute in Leipzig, far away from Munich, where I lived, where they had a cognitive neuroscience department, and there was a neurophysics department headed by Bob Turner. So I applied there to do a master project, and then I just went into it. I didn't know that kind of MRI is something where you need physicists, or what MRI is, or that there's something like fMRI. I just tried to be useful by being surrounded by people who work on the brain. And then, yeah, the rest is kind of just happened from that. I guess I was lucky. There was a lot of serendipity that I was at the right place at the right time, because in those days, 2012, they had a 7 Tesla scanner, which is one of those very strong magnets to do kind of high resolution MRI. This is much stronger than the conventional kind of 3 Tesla or clinical 1.5 Tesla scanners. And in those days, there were already a handful of 7 Tesla scanners around the world. So it was kind of a rather established method already from the engineering perspective. It was not a playground anymore for the engineers to just see if you can build this machine, but it was already starting to get useful in the sense that you could sit there and get an image kind of on a key turn button press basis. Still, it was not really established enough that it was useful for kind of cognitive neuroscience, for that matter. So nowadays, when you buy a 7 Tesla scanners, when a hospital buys one, or fancy, prestigious university buys a 7 Tesla scanner, they rather treat it like a money-making machine. Like if you want to use it, you need to dedicate a lot of your grant money for that 7 Tesla scanner because it's expensive. So in those days, it wasn't like that. It was kind of a new technology that we just figured out, and it wasn't really used that much. And I could sit there in the nights and evenings to kind of learn about 7 Tesla. And after that, it just started to explode. And nowadays there are, I think, 127 Tesla scanners kind of sold around the world. And there's a lot of demand for people with kind of skills that know how to use the 7 Tesla scanners, for that matter. So I was lucky to be there, and I learned the skills that are now under high demand, for that matter. So that's kind of how I went into brain physics.
But did you have any educational courses in like biophysics or anything like that? Or was it, was it like you did, I don't exactly know what it means to study physics in Germany, but typically in Germany, if they ask you to study a thing, you study that thing and not much else. I'm just curious, with what kind of background did you go into this, and kind of what were your expectations of the field and what you were going to do and that kind of thing?
I didn't really had a grand plan, kind of that I kind of where to end up or even to become an academic or anything. It just happened. I like being surrounded by interesting people or intelligent people and people that I learn from. Physics was just something I was good in school. So in Germany, how does it look like studying physics? It's pretty strictly structured. So there was physics and basically nothing else. So quantum mechanics and thermodynamics and kind of a bit of cosmology and those kind of things. It's only then for the kind of bachelor thesis work or the master thesis work where you can kind of specialize a bit more. And it was fairly flexible with respect that I could actually, while studying in Munich, could go to a Max Planck Institute in Leipzig and then kind of find a way to ask another supervisor to be the official supervisor. And then while I'm actually working on something else in a different city, as I said, I didn't really know a lot about MRI. It maybe was mentioned in my curriculum once in a part of a lecture that, hey, you can use these spins of protons to actually produce medical images. And that was it. In fact, there was a lot of serendipity in that they were talking about, when I found it on Google, that the Max Planck Institute for Cognitive Neuroscience in Leipzig and Brain Science was looking for master projects. They had a job ad saying that they are interested in adiabatic pulses. And I figured adiabaticity, I know adiabaticity, which is basically when you pump like in your bicycle pump when it gets hot, right? But when you move something faster, then there's a thermodynamic equilibrium. And so I thought, I'm working on this. Okay, fine. I know my thermodynamics, but it turns out that adiabatic pulses are something completely different. Namely, it's when you, in MRI, you kind of sweep your frequency, off-resonance frequency in a way like slower than the usual Lamour frequency of the spins for conventional excitation pulses in MRI. So it was just random. I still I never took formal classes of brain science. It's something you could catch on as you're working in this discipline. And maybe it's also kind of one of the reasons why I haven't left this discipline since 2012, because it's so multidisciplinary. So there's always you're always kind of the smartest person in the room because you're the only expert in that very specific theme of kind of that you're working on. And everybody else knows something else and you can learn from them. And it's a great environment to kind of always combine different disciplines and brain and medical imaging. And specifically with high resolution fMRI that I like to do a lot, there are kind of the hardware aspects. You need to understand how the hardware is built and how it's imperfectly built. You need to understand the vendors, a bit of kind of industry, what their choices are. There's a lot of kind of vendor research interactions. Then you need to understand your MRI physics, which is, I guess, the only thing that I'm really trained at. And until you get to kind of software, to coding, because being in a kind of new discipline and getting new forms of data means that there is no standard analysis method out there. You need to develop it on your own. You need to become a computer programmer until you ultimately kind of end up with a new scientific conclusion at the end. So it's highly multidisciplinary, working as an MRI physicist in kind of neuroscience settings. Mm-hmm. And maybe there is no formal course ever. And I think in Maastricht University, there's some exotic places now that kind of specialized on advanced neuroimaging methods or cognitive neuroscience method for that matter. And usually that's a small part within psychology departments or sometimes medical departments and so on.
I mean, so you stayed in Leipzig. I believe it seemed to have been good enough, at least, that you didn't want to leave. But it was a different topic, though, for your PhD, right? Or at least it ended up becoming that, or...
I think the transition was pretty seamless. So after I finished my master, I kind of formally transitioned to Leipzig to still work on 7 Tesla high resolution fMRI. The theme shifted a bit. I was still working on high resolution fMRI for 7 Tesla, specifically blood volume fMRI. And that was not really by design or anything, or because I had a 5-year plan or vision. It was basically the path of least resistance, as it happens so often, I guess. And it also the reason why I'm still kind of in the field, that as a master student, I learned what I'm capable of and what I'm not capable of. And the people you work with kind of know what you can and cannot do. And then it's the least risky thing to just take a position if there's one available and to stay in that field. And then moving on from there. In Leipzig, I was again lucky to be supervised by or co-supervised by one kind of charismatic leader, Bob Turner, who was flying around the world and giving keynote lectures and then kind of showing my results in his slides sometimes. And he kind of put me on the map. And then suddenly you build a network, and then there are people interested about your work. And then the easiest path of least resistance is then just to stay in the field and do a postdoc because other people know what you do and so on. It would have been maybe smarter, I don't know, but it would have been kind of a bigger jump to leave academia, to change the field, or to go into industry and kind of jumping in the cold water and trying something completely new, which I didn't do. So I'm not here today as a Layer-fMRI researcher simply because I always wanted this. It's just that it happened to be, and it was always the path of least resistance and a good chunk of serendipity.
Yeah. So one thing that's probably going to become abundantly clear as we talk today is that although I've heard a lot about fMRI and I've occasionally read about fMRI, I haven't actually done much fMRI myself yet. It's going to happen at some point, but so I thought I could use that to ask a couple of introductory questions as we go along. And one of them is kind of, okay, so I understand 7 Tesla has more Teslas than a 3 Tesla scanner. That much I understand. From what I understand, for example, it's not exactly the way that it's just the same thing with a higher resolution, but it's a bit more complicated. So maybe what are maybe first, why try and do 7 Tesla, and kind of what are the main advantages over 3 Tesla, and maybe also some of the stuff that makes it a bit complicated.
There are multiple angles why 7 Tesla is interesting. Like, first of all, it's a stronger magnetic field strength, so it increases the signal like substantially. So usually in MRI, we are measuring magnetic fields, specifically the protons in the water molecules aligned to the external magnetic field. And however, it's only a small fraction that kind of aligns. Most of them are still random, and because they have temperature and kind of flip around. So the stronger the magnetic field you have, the more of these protons tend to align along the external magnetic field, and the more kind of induced magnetization you have available in diamagnetic water, the higher your signal that you capture at the end. And that's an advantage, right? You have more signal, and you can use that signal for all kinds of things. In fMRI specifically, we are limited by signal strength, SNR, when we go to high resolution, because then the voxels, the 3-dimensional pixels, are getting smaller and smaller, and we have less magnetization per kind of unit of information. And then going to higher field strength, 7 Tesla is helping a lot. And so I think actually a lot of the kind of drive for 7 Tesla was motivated for high resolution fMRI, as it often so is. So high resolution fMRI is, from the vendor perspective, from the companies of Siemens, GE, Philips that built those scanners, they don't really care about high resolution fMRI like at all. They think the big market is in clinical imaging. And still kind of 7 Tesla as we have it today probably only exists in this form because people wanted to do high resolution fMRI. So high resolution fMRI is kind of a technology driver, because in the early days, for example, in Minnesota, Camille Ugerbil, they were interested in high resolution fMRI and pushed the vendors to go to 7 Tesla. And then now 7 Tesla is kind of an FDA cleared medical product specifically for applications in MS, like structural imaging, or for cartilage, those kind of things, even though originally it was coming from the domain of fMRI. The big challenges of fMRI, I guess, are currently that they're more expensive than a 3 Tesla scanner. And so it's always kind of a rich man club, and I'm keeping track of all the 7 Tesla and ultra high field scanners around the world, and I think there are 126 right now that I have on a little Google map. So it's still not as much as kind of 3 Tesla, and it's kind of the prestigious institutes. It's not really a kind of something that's available to the kind of researchers in Africa and other countries. So maybe that's a kind of disadvantage to some degree. It's not really diverse. Another disadvantage of 7 Tesla are kind of engineering challenges, which again brings back maybe the vendors at the end. Because at 7 Tesla, the higher the field strength you go, the faster the magnetization precesses, like the spins, how they rotate in the external magnetic field. And the higher the frequency, the slower the wavelength, according to Einstein's equation. And this means that at higher field strength, the wavelength becomes shorter and shorter. And ultimately, we are in the range of centimeters where we have microwaves. Like microwaves or phone waves are in the range of a few centimeters, and they are not ionizing, so they're not dangerous to destroy your molecules, but still they carry a lot of energy, a lot of heat. So at 7 Tesla, as we go to kind of magnetic field waves that are in the range of 10 centimeters to a meter, they start to approach the spatial scale of the head. So sometimes they are kind of constructive and destructive interference that, like, the center of the brain seems to be much brighter than everything else. And that's a problem for medical imaging. Radiologists don't like that. So there's technology around that. Other limits of 7 Tesla might be that you just are at a higher risk of heating up the sample. So there are certain legal limits of how much you are allowed to heat a tissue, namely by 1 degree Celsius, which is the same legal limits for our cell phones. And this means that we just cannot use as much RF energy, like a signal transmission and reception for MRI, as we could at 3 Tesla, which is something we need to deal with. So there are kind of technical engineering limits that are kind of being dealt with. And the reason why the vendors come in here is because the vendors don't really care about that so much, because for conventional clinical imaging, it works good enough. They're not as limited by those factors so much as we are with high-resolution fMRI. So from the vendor perspective, that's basically a solved problem, and they don't develop it further, even though it would be easy to use advanced engineering skills to solve all the 7 Tesla issues as we have them.
Okay, I just have to interject because the way you phrased it, it sounded like you said Africa was a country, but I'm pretty sure you're aware that it isn't.
Yes.
Yeah. And just for anyone listening, I'm pretty sure Renzo's aware of that when you said Africa, and other countries. Yeah. So this is one of those fun things that I didn't. So, I've started helping people collect data for fMRI and that kind of stuff because, you need 2 people in the room and that kind of thing. So I've started helping some of that. And until I did that, I didn't realize that the brain heats up when you MRI scanner. And this was actually been one of the questions. So from what I understand, roughly the time it takes to heat up a brain with a 3 Tesla scanner, I think is also kind of roughly, to the limit, is also roughly the time that, beyond that, you don't really want to have people long in the scanner because then they just start falling asleep anyway. So it's not that much of a problem. But I'm curious for 7 Tesla, how long can someone be scanned there before you start steaming their head from the inside?
We are lucky at 7 Tesla that usually we are only imaging part of the brain or part of the body. So if there's energy deposited on the head, that's disseminated across the entire body pretty quickly. And so from the legal limits, which I think there are different standards in Europe and US, overall, there's kind of an overall limit of how much you're allowed to heat the tissue. And there are usually safety factors by a factor 10 or more to really make sure that nothing's happening. So usually it's not that dangerous to deposit a bit of energy in the brain because it's highly perfused and most of the energy is just distributed across the body. If you're asking about the legal limits, I think specifically there's a 10-second SAR. SAR is a specific absorption rate. So within 10 seconds, you're allowed to put more energy in if you then allow the heat to be distributed across the body in the next 6 minutes. Then I think there's also a 6-minute and 10-minute SAR where you're also not allowed to exceed certain thresholds. And that's kind of supervised on many levels. Usually when I install a new sequence on the scanner, it needs to be I need to have some energy budgeting. I need to tell the scanner how much energy I expect to be deposited. And then the scanner checks that. And then also in real time, they check how much energy is actually going through the cables. They match it with the expectations. And if anything that doesn't make sense, it shuts down. And especially for newer technology on 7 Tesla, where you have multiple antennas at the same time, there's also the danger that kind of multiple waves are focusing and you have hotspots. And there is a certain way of engineering and safety guards kind of to really make sure that nothing is happening, which it's all a solvable problem, because ultimately those legal limits are really extremely conservative, like by a huge margin. And nobody wants to kind of risk anything. But at the end, I think the better the models are, if the more users are really limited by those legal limits, then the models would be improved and the legal limits could be adjusted and fine-tuned, and they would not just kind of have a ballpark of a safety factor 10 or something. But there's energy deposited. And yeah.
Yeah, I mean, I guess it didn't occur to me that, I mean, it makes complete sense when you say it, that, I mean, related to fMRI, the whole idea of blood flowing through your brain is also that it flows out of your brain again. And then I guess you get new blood that then, evens out with the rest of your body, I guess. Okay, so it's not like when you use 7 Tesla that you're necessarily restricted to, much shorter time that you can give people a task to do anything like that. It's more about the sequence, how you run that. Or...
Absolutely. Like the energy deposition is in a range of a few seconds to minutes. I think the longest scans that most people do is in a range of 2 to 3 hours or so. Well, I think they did dream studies, like overnight scans, which are kind of uncomfortable for other reasons rather than beating up the person.
Do people actually completely fall asleep in the fMRI scanner? That's...
Like I was a test subject. That was a 3 Tesla, where I think I was in the scanner for 8 hours. That was intense. Specifically also because they had EEG on my head, and then lying on top of that was just uncomfortable. They took out the patient bed and put a very soft mattress there, and that was exciting. Yeah. There are a lot of kind of big sampling studies, also kind of overnight studies, where people fall asleep and then they're woken up and then they ask, "What did you dream? What did you dream?" Yeah. But
okay, I know that. But with EEG, I mean, assuming they don't put the gel in, then, because that would just like squish all over for hours. I mean, or do they actually still do the gel with all the electrodes? Because I'd imagine just like, you move a little bit your head and over, it just like melts over your skull.
I don't know all the specifics. There are it is a pretty big subdisciplines of fMRI, like multimodal imaging, where people do fMRI and EEG at the same time. I think there are different kind of electrodes, depends on kind of how the contact is. I think in my case, it was still with the gel, and it dried up and it was uncomfortable. There are kind of more fancy electrodes, specifically with those nets that kind of don't need that gel or different gels. But yeah, it depends. I think there's a lot of room for optimization, specifically the ones at the back of the brain. If you remove those electrodes, then you're not directly lying on top of them, and you don't feel like they're kind of pressing through your skull.
Yeah, that can't be pleasant. Just a kind of final question or two about larger and larger scanners. I mean, is it in theory always better to have a bigger scanner? I mean, taking aside things like costs and that they take up more space and these kind of things, but like from a let's say cost was not an issue and space. I mean, basically, would you always be in? Would it be great for you to always have a bigger scanner, or is at some point it doesn't make that much of a difference, or the pros and cons kind of start to flip a little bit? Or I mean, I'm especially thinking because I did part of my master's at Neurospin in Paris, where they this year had the what it was like 11.5 full Tesla full body scan or whatever it was, and I think they've published something very recently about this. Yeah, so I'm just curious: is more Teslas always better, or?
Like in theory, yes. If you would be in full control of the engineering, then yes. And I think it's just a matter of time. Like I guess in the early days, people thought that 7 Tesla is kind of this weird playground for physicists and it's never going to be useful. And there are all these engineering challenges. And now it's a clinical approved scanner and it just works. With respect to Layer-fMRI in Maastricht, where I had access to a 9.4 Tesla scanner, 7 Tesla and 3 Tesla scanner. And you can run a high resolution layer dependent fMRI on either field strength, right? At 3 Tesla, you just need to average a lot because the signal is noisier. 7 Tesla is kind of established enough that it just works. You upload your sequence and it's a turnkey method mostly in most brain areas that it just works. At 9.4 Tesla, you can even have better signal, right? If you have a whole team of engineers working on it and then having prototype self-built RF coils and then cables around and then some of this breaks and then you have an expert who knows what to fix and then you get this awesome figures and images out of it at the cost of kind of having 2 successful scans per week. So maybe 7 Tesla for Layer-fMRI is kind of the sweet spot. But obviously, at the point when 9.4 Tesla or the 11.7 in Paris will be like straightforward enough, there's a lot of signal to be harvested. Like these Nature Methods papers, images, they look like gorgeous. Or well, they given kind of the surrounding setting, right? They have a lot of issues, of course, and I've seen nicer images at 7 Tesla, but not in the time scale they acquired it. Like they have these multi-echo GRE images in 4 minutes or something. They're like, it takes half an hour for me at 7 Tesla to kind of get to that data quality. So 11.7, where we have, I think, 4 big projects around the world where they're building 11.7s. Paris is the fastest one with the first human images, and or in vivo images in humans for that matter, that there's a lot of signal to obtain. And I think there's even their higher field strength scanners being proposed for the Netherlands at 14 Tesla. And they had a nice proposal also in Germany. So there's always kind of more to further to push. And I'm not sure if it will pay out at some point. It's definitely kind of a new frontier. You will see things that you could not see before. And again, kind of 7 Tesla, like Layer-fMRI is a kind of technology driver for 7 Tesla and other methodologies. So 7 Tesla is a technology driver for clinical field strength. Like all this problem of interference of wavelength that we have at 7 Tesla was only really well described and acknowledged after 7 Teslas were mainstream. And now a lot of this knowledge is being used at 3 Tesla to optimize 3 Tesla and make them more stable as well. So I think there's this aspect that a lot of people just want to see what they see and then go for it. And of course, there is kind of who has the biggest, longest, strongest, and who is the biggest institution. And everybody wants to have the highest magnetic field strength. It is very challenging. Specifically, it's also not kind of so sustainable. These scanners need a lot of helium as well, which is kind of scarce or up and down sometimes. I think for Layer-fMRI, it's not only the field strength itself that matters, but also what you mentioned, like in Paris, they have a whole body scanner, which is ironic because kind of they will use it for head imaging. And so most of the 7 Tesla scanners out there are whole body scanners with a huge bulky gradient that's kind of optimized to be flexible because that's what the vendors want. At the end, however, most of those people use it for head imaging. And if we would make smaller gradients that would just kind of be suited for the head only, we could really increase the kind of the performance way beyond. So a 7 Tesla scanner with an awesome gradient can maybe outperform a 9.4 Tesla scanner. And there are some initiatives about those awesome gradients too. For example, in Berkeley, the Fine-Bergertron, we call it the Impulse or Next Gen 7T, which is lower field strength, but other components of the scanner are really optimized for head imaging, for fMRI. And those gradients are very popular and being sold like hotcakes now.
Yeah, I mean, this is something I find quite interesting. I think it might have been in my episode with Peter Benettini that he mentioned that, you know, the big advantage of fMRI when it started was that the machines already existed. They were everywhere, right? It was just a standard MRI scanner that was in every hospital, more or less. And I guess that's kind of being lost to some extent because now it's, as you said, it's trying to develop it as its own thing and take it to places that maybe a clinician who just wants to see, I don't know what clinicians want to see, but like where the ligament is torn or whatever, I don't know. You know, maybe they don't need, and where they can scan the same thing for a couple of minutes and where they just don't need that kind of resolution and where maybe the extra cost isn't really justified. So I think it's kind of really interesting to see kind of what happens now when, I mean, I guess it's been going on for a while, but when people really take it into a direction for its own sake rather than just because the machine kind of happened to be there.
And at the end, I think it's still kind of a tandem, right? We are in this symbiosis with the vendors. They don't care about fMRI and still there's new scanners being built, but then the vendors kind of do that because they might learn something that they can use and market for a clinical environment. So like a lot of developments, let's say like multiband, maybe you heard about that, kind of accelerated imaging, which was a big game changer in kind of increasing the spatial temporal resolution, was built for fMRI. And then now the vendors are earning a lot in kind of selling licenses and using it for clinical scanners. So it's always kind of this back and forth, even though the technology doesn't really exist yet, still kind of we build it for kind of that purpose and then another field benefits from it and vice versa. And now we benefit a lot from the fact that at 7 Tesla might be very useful for multiple sclerosis, right? You have these veins very visible at 7 Tesla, not for 3 Tesla. So we can build those, like we can buy those 7 Teslas, and we don't need to build them ourselves, even though they might originally have been built for Layer-fMRI. Now they are kind of a factory clinical product, and we can just buy that. And from my time as a physicist, and I learned how complicated it is when you cannot kind of buy something, right? When the Large Hadron Collider had a quench, like the superconductivity broke down and it tore a part of the accelerator apart. You needed an entire team of physicists, quantum mechanics to know about Cooper pair superconductivity, repaired it. It took 2 to 3 years until they could restart. Everybody else, thousands of researchers were waiting. So in MRI, we are lucky enough that we kind of can piggyback on this kind of clinical scheme from the vendors. They benefit from us, but also we can just buy a scanner. Yes, they're expensive, but it would be like orders of magnitude more expensive if every 7 Tesla Layer-fMRI center would need a team of physicists that basically wire their magnet and know all the ins and outs. And yeah, it would not be as stable as kind of a factory production. So it's still kind of true that we benefit from them and they benefit from us. Yeah.
Brief question, just because from what I understand, pretty much, the bigger the magnet, the bigger the machine. Is that like a necessary thing, or is it just we haven't figured out how to do the engineering better? I'm just curious because, like, at some point, I mean, I think I've seen the images from Paris. It's it's an enormous machine. You can't just put that into the cellar of a hospital, right? And so I'm curious, like, is that something that's just like always going to be the case, or do you think we'll be able to? I mean, I guess it's always a risky question to say, no, this isn't possible, because then there's always going to be someone's going to have an idea in 50 years and do it. I guess like with MEG, we didn't think that probably when they started that now you could do it in like the size of a remote control and put a bunch of those around your head. But yeah, so I'm just curious because, I'm just curious. Do you think that's always going to be the case? Or are we going to figure out how to make smaller magnets so that, we can have a super small fMRI?
It depends. It's less a physics question than kind of marketing engineering. The one in Paris is exceptionally huge. The 11.7 Tesla that we have here at NIH, that's not on 11.7 because it quenched again while ramping up beyond 11, but not at 11.7. That is a head scanner, and it's way smaller. It's almost as big as a 7 Tesla scanner. Now, the plans for this 14 Tesla in the Netherlands is actually as the size of 3 Tesla scanner, because they're using a completely different technology. They're not using the conventional superconducting wires that are kind of cooled with liquid helium. Usually those wires, they lose their superconductivity beyond certain field strengths, maybe 10.5 or so, where you need to start to pump helium. So at the temperature of the 4 Kelvin, when helium evaporates and cools the magnets, then you cannot keep up with that magnetic field strength. So you need to basically reduce the pressure of the helium, and then it evaporates sooner, and you can reduce the temperature even further. So now the new design on the 14 Tesla in the Netherlands is using a different material, these high temperature superconductors, where it's a different technology. Nobody has ever done it, so who knows if it's going to work. But if you look at those marketing pictures and how they envision it, it's kind of a person, and next to it there's a scanner of the size of a person, and it might be kind of more complicated to ramp it up and to build it. But as soon as it's on field, then it might be kind of more stable. That's what I've heard in the lectures so far. But it's all kind of in the concept stage. They got the funding. The magnet doesn't exist yet, though. But in that case, no. The scanner is tiny.
Okay, cool. Yeah, I just was curious. I was curious whether, sometimes you just have this like physical requirements and just that's the way it's going to be. But okay, cool. Yeah, I mean, so I initially invited you to talk about Layer-fMRI. We haven't done so far. How did Layer-fMRI enter your career?
I think it was always there. Layer-fMRI was always part of fMRI in itself. I think like fMRI has the unique feature that it has high spatial resolution, like more so than EEG or MEG or PET even. So I think among the many disciplines of fMRI method development, high resolution fMRI was always kind of let's say the discipline supreme or something. Like every center that was involved in fMRI development, world leading center that invented fMRI, are still pushing for high and high resolution because it has the highest promise of showing something completely new. Nobody could ever kind of see the living human brain at this spatial scale with any other method. So pushing for resolution makes a lot of sense. I'm not saying that maybe I should use a metaphor. Like there are all different disciplines in fMRI method development. Some people look at quantitative fMRI for clinical applications, white matter fMRI, or some people look at very challenging spinal cord fMRI, and those kind of, which are kind of dedicated people that know the literature and are innovative. And similarly in high resolution fMRI, but high resolution fMRI is just always getting more attention. So since the 90s, people push resolution, and so did I. Always try to push as much as I could, because why not have higher quality, higher resolution data? So in some sense, it's like in the Olympic Games, right? You have the fastest man alive, right? Usain Bolt, everybody knows kind of those disciplines. But do you know the name of the fastest sailor or the fastest discus thrower? So high resolution fMRI has always kind of got more attention than other disciplines. So I started on blood volume imaging, which was a bit more quantitative, and I just pushed resolution as everybody does and kind of entered into high resolution. Also because it's a kind of unique selling point of having a high field scanner, and it has the highest chances of just seeing something that nobody saw before. And there's a lot of information at these spatial scales of kind of the few hundred micrometers in the sub-millimeter scheme, where kind of all this cartography and way of doing fMRI as the conventional field is doing is fails, right? You get more information on how the brain area is involved in a given task at high spatial resolutions. So that's why I kind of stayed there, and it was valuable and perceived as valuable. And so I could kind of have positions and have a job.
That's nice. So is Layer-fMRI then, I mean, how is Layer-fMRI then different from just high resolution fMRI? Or is it just a marketing term? Or is there, what's the precise difference between, just high resolution fMRI and Layer-fMRI?
There isn't. No, almost there isn't. No, it's a marketing, well, it's flashy. I think actually high resolution fMRI started mostly with columnar imaging. So where people looked at layers, but not see how the layers are different, but basically how the layers are the same. Ocular dominance columns in 2007, 2008, there were kind of iconic images of people also looking at orientation and ocular dominance columns. Also before that, I think only then later the kind of basic cognitive neuroscientists came along and used it a lot for kind of their circuitry questions. In Layer-fMRI, they specifically were looking into things like feed-forward feedback, which is kind of different layers, like feed-forward input, like in the visual cortex, when you have input, sensory input from the eyes, go through thalamus into the middle layers of the visual cortex, whereas upper and deeper layers are mostly receiving feedback from higher cortical areas. So a lot of people started looking into Layer-fMRI from that angle. There are different layer models, like there's predictive coding, where people predict that kind of prediction errors are estimated in different layers than others. There is kind of modulations of brain activity with respect to attention. There are less cognitive neuroscience researchers that are more interested in kind of how the biomechanics of the brain works, that look at kind of vessels versus non-vessel voxels, like superficial kind of stuff that happens above the cortical ribbon versus stuff that's within the cortical ribbon, which is some form of Layer-fMRI. Currently, it seems that most high-resolution fMRI is really done on the layer level. And that's why kind of that's a marketing thing. People don't like it because we're looking at, or some people don't like it, and electrophysiologists don't like it because they say, well, it's not true layers, right? If you look at 3 layer groups across the cortex, that's not the Brodmann layers, the cytoarchitectonical Brodmann layers. So some people call it laminar fMRI, which is just a Latin word for it. And some people call it mesoscale because it's not at the microscopic scale of the neurons and not the macroscopic scale of the brain areas, but it's kind of somewhere in between. But it doesn't mean anything, mesoscale. It's just middle scale. Like in physics, when you talk about mesoscale physics, you're not in the range of planets and not in the range of atoms, but you're in the range of few kilometers of weather and those kind of things. So every discipline defines the terms as they want to. I think Layer-fMRI is a kind of catchy enough name, and it's kind of it shows what we are aiming for. And I have a blog post about the terminology, but it's mostly marketing. Yeah. And then some people kind of the purists, they call it cortical depth dependent fMRI, but that's a mouthful, right? It's not a cool Twitter handle.
Yeah. Okay, so that was one question, like laminar and Layer-fMRI then is the same thing, or?
Yes.
Okay. But like presumably you are still focusing on layers rather than, areas of the brain that don't have layers. You could also try and get more precision in the hippocampus or whatever. So I mean, it's not just marketing, right?
No, it's not. And I think the most valuable immediate additional information that high resolution can give us is by looking at different layers, because these different layers, they have different neural populations, subpopulations that kind of do different things. So by looking at layers, we can get a lot of information that we cannot get with kind of looking at the big structures of just the brain areas. Maybe to give an example, like the study that convinced me that Layer-fMRI gives us more than kind of cartography, blobology, fMRI, is by looking at the simple example of the motor cortex. Like in the motor cortex, it's close to the antennas, it's perfect signal, it's pretty thick. The superficial layers, layer 2 and 3, they have a lot of input. Like when you reach to grasp something, for example, you need to have certain motor planning input, then there's sensory feedback. That all comes into the superficial layers to combine that. And then the deeper layers in the motor cortex, they have these output circuits, recurrent circuits that have the gigantic pyramidal bed cells that have the direct connections to the spinal cord, and then they trigger the muscles to move. So now, if you have a motor task and do fMRI, which area do you see activated? Of course, the motor cortex, right? But it doesn't really tell you that much. I like this metaphor of trying to understand how a truck engine works by looking at it with an infrared camera. If you want to understand kind of the truck, it has all these different components. How does it work? During driving, we see, okay, the front seems to be heating up, right? It consumes a lot of energy. Yay, it's cool to see it. Or when you push the brakes, something else seems to be heating up. And that's kind of the level of kind of fMRI at some point. So in layer-dependent fMRI, we get to a different spatial scale of the kind of microcircuitry. We not only see kind of if the front is heating up, but more kind of why it's heating up. So for example, in the motor cortex, when we ask people to do a finger tapping, we see that the cortical input and the corticospinal output, both layers are kind of activated, both layer groups. Now, when you want to spice this up, make it a bit more neuroscience sexy and ask people to not tap their fingers, but just think about moving their fingers, like mentally. They lie there, don't move their fingers, and then what area would you expect it is lighting up? Of course, the motor cortex, right? The circuits are there. It's responsible for hand movement. So, of course, in both cases, in conventional resolution fMRI, we see, okay, the motor cortex lights up. So we didn't really learn a lot, right? Maybe the activation strength is different, but overall, it's frustrating how similar the brain looks given this different behavior. And this is, I think, where Layer-fMRI comes in, because for the imaginary tapping, as being done by Andrew Pizzichetti, maybe inspired by Robert Turner and Robert Trampel in Leipzig before, they found that for imaginary tapping, it's actually only the superficial layers that are being activated. There's no output, right? The muscles are not being engaged. So Layer-fMRI tells us more than just whether a brain area is involved in a certain task, but kind of how it's differently involved for certain tasks. And there are a lot of features that are interesting for cognitive neuroscientists that always engage the same brain area, but in a different way. Let's think about attention, right? If I focus on the top right of my screen now, the bottom left of my visual cortex will be differently activated if I pay attention to it. But you cannot answer attention with cartography, right? There's no attention area, right? It's rather in the visual cortex, it's kind of the feedback input that activates and enhances the activity in the respective visual cortex. And that is not really driven by feed-forward input, like from the eyes. The input from the eyes into the middle layers is the same. It's only the regulatory feedback input in superficial or deeper layers that is being kind of differently activated. So you can look at those kind of non-local features, which is specifically also interesting if you want to understand something like multimodal integration. There are a lot of areas that are engaged independent of which sensory modality you use. Let's say V5 or planum temporale. Those are areas kind of responsible for perception of motion. You can perceive motion with kind of having moving dots on the screen or with auditory tasks where you hear something moving. And then with layer-dependent fMRI, you can kind of answer those questions on how there's feed-forward coming in directly from the sensory areas, or if kind of how much is feedback coming in from another modality and how it's integrated together, which we're also looking at with Marco Barilari in Belgium, looking at blind people. Other applications where layer fMRI is particularly useful is kind of things like psychosis, right? When you have hallucinations, where there's, of course, auditory activity for auditory hallucinations in the primary auditory cortex, even though there's no direct feed-forward input from the ears through the brainstem going to the ear. It's a misbalance between kind of sensory input versus kind of other cortical areas taking over that area. And there are a lot of theories in psychosis and kind of in psychiatric research, whether this is coming from too weak feed-forward input or too strong feedback input. And layer fMRI can ask all those questions beyond just saying whether or not there's a brain area involved in that certain task in like cartography. And still having the kind of unique advantage that we we can do it in large coverage. Like many of the things that I mentioned, you can investigate in animal models with electrophysiology, right? The so-called true neural activity, as they call it sometimes a bit righteously. And Layer-fMRI is kind of in between those different disciplines. So the true value of Layer-fMRI might be to kind of bridge the gap between cartography and kind of the cellular circuitry electrophysiology. And maybe I can use another metaphor here that specifically in the context of being at NIMH, we know that most of psychiatric diseases are network diseases, right? And so that it's not a single area that's kind of screwed up in schizophrenia or autism or whatever. It's a network that's screwed up. So how do you investigate that, right? In fMRI, we kind of see that the network and that it might be screwed up, but we don't really know why. And maybe in the metaphor, let's pick a network that everybody knows, like the street network of the United States, right? If we can look at the connectivity of Chicago and New York or whatever, and look at the storage halls and how much connectivity is going on there on the big structures, right? The cities. And then when the network is screwed up, we don't really know why. Is there a traffic jam, for example? And then the connectivity is broken. So just looking at the big cities and that the network breaks down doesn't really tell us that much. Now, electrophysiology, they're kind of looking at a true neural signal at the smallest mechanistic level. In my metaphor, that's maybe like the brake pedals of the cars, right? The ultimate thing that makes cars not go and not connect those two cities is because people press their brake pedal, right? So the true mechanistic reason why the network breaks down is the network pedal. So we should take them apart and look at them in the microscope, which is absurd, right? So I think that the mesoscopic regime, not only looking at the cities and not only looking at the brake pedals, but trying to understand why we have a traffic jam, why this network is corrupted or screwed up in a certain disease, is the mesoscopic regime. Like in Google Maps, when you look at your traffic pattern, it tells you the parts where it's red and where it's orange, and it tells you which lane, right, which direction. And this is the unique information that allows us to better understand why the network is screwed up. So in layer-dependent fMRI, we not only know if two areas are connected to each other, but we know that the layer that is responsible for this connectivity. So for example, in hierarchical brain systems, we know that like early visual cortex sends feed-forward input to the mid layers of higher order areas. And the feedback from higher order areas to lower top-down feedback is coming in upper and deeper cortical layers. So we learn something about the causality of this connectivity. We not only learn if they're connected or not, and how strong this connection is, but we learn something if it's the forward or the backward connection that's kind of screwed up. We still don't know how to fix it, but it gives us a unique spatial regime to kind of bridge the gap between human neuroscience and kind of the cellular neuroscience. And they don't really talk to each other a lot. And it's a huge opportunity to kind of fill this gap of this medium mesoscale regime, let's say, of a few hundred micrometers.
So how well does the precise imaging of layers work then? I mean, is it, I think you mentioned earlier that some people might say it's not exactly Layer-fMRI because it's not all the layers you might want. So like, how well does it work already?
Well, I use the term layer as a loose term, and maybe I should say call layer groups. And I guess it always works as precise as your model is. So I mentioned a lot that we have this kind of feed-forward model, Fellman van Essen model, which I think is also used in predictive coding. Friston picked that up, that kind of a certain feed-forward and feedback is coming into middle or upper and deeper layers. That's a 3-layer model. And of course, I can only be precise as this 3-layer model. Now, when we have 0.8 millimeter resolution for a 2 millimeter thick cortex, that gives us roughly around kind of the right spatial scale to kind of answer anything about the 3-layer model. We are not really solving the 6-layer model, but we don't have a good model kind of for the 6 individual layers differently. There are other models, like in the frontal cortex. Actually, with Emily Finn, your previous guest in the podcast, we were looking at Layer-fMRI in the DLPFC, dorsolateral prefrontal cortex, where we are looking at a more input-output model. There are these upper layers that have the Q cells, delay cells, that kind of keep a string of letters, or think about your phone number. They keep that information in your working memory for a few seconds, and then the deeper layers are sent the output to the motor cortex if you need to press a button or if the monkey needs to do it. So there's kind of the input-output model. There's the feed-forward feedback you mentioned hippocampus. It has layers. It's not a neocortex. It has 3 layers, right? Okay. And there are these kind of in the entorhinal cortex, which is not hippocampus, but kind of the relay station, we have kind of the upper layers and the deeper layers do different things with respect to memory. There's the memory encoding and there's the memory retrieval. In hippocampus, for the different sub areas, there are also the different upper or deeper, or let's call it inner and outer layers in hippocampus that are more responsible for different pathway of kind of pattern completion or pattern recognition of kind of events or pictures or whatever. So in that sense, how precise is it? Kind of it can be precise as your model is. Sometimes I got like a curse, and it's a curse and a blessing to work in something new. The curse is that you need to defend your stuff to other disciplines that are kind of established. And sometimes when I'm getting towards kind of circuitry, I get reviewer feedback that people say, yes, you have reduced your 3 millimeter voxels of 700,000 neurons now to 1,500 neurons of one voxel. But you cannot be so naive to say that all these neurons are doing the same thing. So it's in that aspect, they're right? It's still not exact. And even kind of, if I would be able to resolve every of the 6 different layers, I cannot be so naive to assume that all the neurons in the given layer are doing the same things. There are different populations in every layer. Anyway, so at the end, I guess the question is kind of the model that makes sense for you. And I think these standard models, input, output, feed forward, feedback, are quite successful right now. Ultimately, there are still simplifications. That the big advantage is that they are better than just assuming that every neuron in the entire brain area is doing the same thing, or that every neuron across the entire cortical depth is doing the same thing. Kind of the 1-layer model is obviously not as great as a 3-layer model, even though it's kind of not super precise just yet. And ultimately, I think we are maybe lucky that layers are just kind of a basic neural building block. If you resolve it further and further to kind of then the cortical columns or the cortical layer, I'm not sure if you would gain that much kind of on a kind of looking at the whole brain perspective. Layer-fMRI sometimes is criticized as fMRI that it's an indirect measure of neural activity. You're not measuring the neurons directly, but also I'm not sure if we really want to. Like, being a physicist here, I think whenever people call their kind of what they're working with signal or activity without even a physical unit attached to it, they don't know what they're talking about. And we call it signal, bold signal, or neural like fMRI activity. And I think that's right. But what is the unit? The ultimate truth neural. As a physicist, I think the ultimate unit that we're interested in is energy. It always comes down to energy in the universe, in the brain. And I think fMRI just gives us that, right? fMRI is a hemodynamic response that's triggered by oxygen consumption of the neurons, right? So if we would have in kind of 100 years in the future, if we would be able to measure the neural activity of every single neuron in the entire brain, and not only looking at multi-unit activity and looking at frequencies and coherence, if we have all information about every neuron in the entire brain, what would it give us, right? How would we take advantage of that? How we distill it down to a kind of a meaningful understanding of how the brain works? And I think ideally we would want to have a conversion function that converts all these different measures of spiking, of different frequencies, slow waves, faster waves, into something that kind of tells us something about how much information is processed. So we would like a conversion from kind of all these different things that the neurons do, where we don't really know which one of those measures has the most information in there. Some of it might just be smoke from kind of actual other work that's happening. So I think energy is a good unit of activity, and fMRI just gives us that at the spatial scale of the basic neural building blocks, the layers and the columns. So yeah, to answer your question, how precise is it? It's precise as your model. And I think that the model of the layers as kind of basic neural building blocks and looking at the energy, how much those neural building blocks use, seems intuitive and plausible to me. Yeah. Without needing to discredit kind of electrophysiologists. Sorry, it's very valuable research, and somebody should do it. Yeah.
So I mean, you said it's as precise as your model, but you can't do all 6, right? Or did I misunderstand that then? I mean, there's still like a limit to this, right?
Yes, there's this Moore's law of fMRI resolution, where I believe so far it's right that every decade we get an order of magnitude in voxel volume reduction. So in the early studies from Peter Banettini, I think they had 200 milliliter voxels, like huge slices, for other reasons, because they didn't know where the
milliliters. Okay,
as he explained in your podcast as well. And then there was a lot of hardware improvement. In the last maybe 20 years, not so much hardware. It was mostly kind of sequences and reconstruction improvement. But still, we are kind of getting higher and higher resolution. The highest resolution I've got was 0.39 millimeter isotropic at the Berkeley scanner, where we could look at some of the thinnest cortices in the brain. Motor cortex is easy. It was an easy place to start because it's 4 millimeters thick. In the visual cortex, we are in the range of 2 millimeters. And there it's very hard to distinguish kind of even the different layer groups like feed-forward and feedback circuits with Nyquist sampling, where you have a layer, a space in between, and then another layer, and so on. And there with 0.4, maybe better with 0.35 millimeter resolutions, you really start to separate the kind of the closest units to begin with. And you're right. I think nobody has ever done fMRI with resolving the 6 layers, though I'm not really sure if it would get us so far. Like layer 1 is tiny. It doesn't have much interesting stuff going on anyway. And then maybe layer 4 instead is much more interesting. It has different groups like 4A, 4B, 4C, and then there are different Cs that have the different kind of feed-forward input from the thalamus in the visual cortex. So I think the highest we currently can hope for is kind of to have 3 different layer groups and have them Nyquist sampled. Not only have them at 3 different voxels, but actually voxels in between that are not really dominated from either one. And I wouldn't really know what to make out of the sublayers. Also, very often these different layer groups have huge kind of recurrent connections. So you cannot really, with fMRI timescale, separate them anyway. So in the motor cortex, when I talked about the output circuits of layer 5, I was specifically thinking about layer 5B and 6. So if 6 is activated, it activates layer 5 and so on. So I'm not really sure if we can tease them apart. Maybe we can a bit. But yes, we cannot resolve all the 6 layers just yet. And I'm sure in 10 years we have higher resolution, and then we will see if it's useful to go even further or not.
Okay, I didn't realize there was such a clear progression. I mean, I guess it's been fewer cycles than with actual Moore's law, but if it's on the order of a decade. But okay, that's so cool. Yeah, I mean, one question I had in general is basically like whether layer-specific information, in a sense, is equally applicable or useful for different types of research. I mean, for example, as I said before we started recording, I did one of my master's projects on predictive coding and, so in perception in particular. And so from that, it's very obvious that it's very useful and that, that it would be supremely useful. And especially like some of the clinical applications you mentioned were also some of the things I was thinking of. It's built into the theories of like why this methods would be useful. Now I work more in like value-based decision-making. And there I've, read less about, I can't remember if I've read anything. I don't know, maybe I just haven't read enough, but I'm at least not as familiar with layer-specific information. And so for the kind of stuff that I might be doing in the next couple of years, I'm not entirely sure how useful it would be there. But so yeah, that's basically my question. I mean, presumably there are always things where it's more or less relevant, but yeah.
I'm not a kind of decision expert myself. At the end, if you look at circuitry, Layer-fMRI will be useful because you kind of know which area kind of sends feedback in one direction or the other. If you kind of know your circuitry from tracer studies beforehand. Another angle would be that high quality data are always better than low quality data. So having this additional information of layers is always kind of more useful. Even if you don't have any layer questions or the power to kind of look at Layer-fMRI noisy signals and with kind of cognitive tasks like decision making, it can sometimes still be useful to look at layers, not from the perspective of kind of your layer model, but basically from the perspective of your noise model. Like that on the cortex and is on top of the cortex, above the surface, we have a lot of vessels. Like we have arteries, they pulsate, there's CSF floating around with respect to kind of respiration and heartbeat. This introduces a lot of physiological noise. And as soon as you have big voxels and they have partial voluming, a small fraction of that voxel contains this noisy signal from CSF that has nothing to do with your task, it kind of compromises the signal that you care about, the bold signal in the deeper layers of the cortex. So some people also propose to do layer-dependent fMRI specifically for denoising, basically even at lower resolutions, maybe 1 millimeter or 1.5, just do smoothing, not like Gaussian as some people do it, but basically only smooth within a given cortical layer. If you even if you don't really resolve layers at the end, you basically remove the noise that's above the cortex, the kind of superficial most layer to some degree. Right? So there's always kind of something that Layer-fMRI could give you, I guess.
Yeah, just to focus on one of the early things you said, I guess that's also like one of the points you made earlier, but I think maybe that's worth highlighting. One of the main advantages that we kind of have a general understanding. So this is a question that we have a general understanding of that actually everywhere in the brain, specific layers do specific things. So for example, if we see that, this area lights up, then with layer specific information, we might be able to, could we be able to then say more that, okay, we think it's just processing this information, or it's receiving it or sending it? Again, like in a predictive coding sense, I understand more what like the, feed forward and feedback things would work. But if it's not about prediction per se, then I'm just trying to figure out like what would it tell me exactly if I know that the information is received rather than sent? Because presumably, if it's received somewhere, it has to be also sent from somewhere, right?
Right.
Okay. So then you know from where to go. Okay.
But even kind of if you don't care about layers at all, going to high resolutions, like even from a cartography perspective, you can kind of better delineate the information processing within the two-dimensional cortical sheath. And going to high resolution, there's a lot of kind of open ground where nobody really knows what to expect. So we have been quite lucky, like even in simple things, like in the motor cortex, that if you don't care about layers, and actually in that study we were smoothing within each column to completely get rid of the layer signal. Just going to high and high resolution allows you to see new things that you might not have been expected, and then you get more kind of hypotheses from that, and go on and so forth. For example, in the motor cortex, we found that as you go to high and higher resolution to look at finger digit representation, for example, in the sensory cortex, everything was like we expected it, right? Neighboring fingers were next to each other in the brain, and we have this kind of homunculus model. In the motor cortex, it was completely messed up, that as you go to high and high resolution, we actually see that, yes, the different spines are kind of next to each other, but as you go to the kind of microscopic, mesoscopic regime of the columns, you see that within the hand knob, there are multiple representation of each fingers. And the motor cortex, even though in the textbooks is kind of simplified as this homunculus model, it's actually more a muscle map, not really a homunculus map, but there are kind of multiple mirrored finger representations within the hand knob that with conventional resolutions you just didn't see. And actually, also in the original literature from Penfield's textbooks, of course, are always oversimplified. And there were already indications there that the same neurons are actually responsible for multiple fingers. And it makes a lot of sense to kind of now then rethink the motor cortex as an action map. If you use the hand rather for grasping versus retraction with those muscles for extension or flexion, they are differently represented. So even though we didn't really expect that and just wanted to see kind of the topographical representation for a task where we kind of knew what to expect, going to a high resolution allows you to see something new and then ask new questions and then build new hypotheses based on that. So no matter what you're doing, if you have good signal and you can do it at layer resolutions, then you might see interesting things that are worth pursuing, I believe.
So how do I do that? Do I have to... Okay, maybe first question, I believe you already kind of mentioned it very briefly earlier. Do I need a 7 Tesla scanner or higher to do this?
A 7 Tesla is helpful.
In general, it's good to have one.
It's good to have, like in most brain areas, let's say. Overall, the field of Layer-fMRI kind of is still exponentially growing so fast that it's kind of outrunning the ultra-high field growth. Like layer papers, there are about 260 right now, and they still double every 4 years or so, 3 to 4 years. In the ultra-high field scanners, only double about every 7 years or so. So you're kind of running out of scanners. So there's a kind of a pretty big drive in the field to also move this to 3 Tesla scanners, which not only makes it more accessible to continents like Africa or other countries, it also kind of makes it more diverse and allows kind of more people to use that technology. So in a recent study with Martin Grumblicher in Salzburg, we kind of quantified the usability of layer-dependent fMRI, blood volume fMRI, which is what we did. I do a lot at 3 Tesla, and it turns out, yes, you need to scan a bit longer, maybe 2 times, maybe 3 times longer, but you can do a lot at 3 Tesla as well. And this is even if you have the high ambitions to see kind of voxel-wise activity in a kind of entire volume-based analysis where you want to see for each voxel how activated it is. Very often, neuroscientists don't really have kind of the need to look at kind of maps, so to speak, in the 3D volume space, but often they want to know if that layer in a given brain area is acting different than that different layer in that brain area. So you have the luxury to just run very high resolution fMRI and then just average all the voxels in a given layer group, compare them to all the voxels in a different layer group. So even though you don't have enough signal at kind of noisier field strength of 3 Tesla, if you average a lot of voxels at these high resolutions, you still get a lot of signal back. And very quickly you are in a noise-dominated regime where you're not limited by the thermal noise of the scanner, but rather limited by intertrial noise or physiological noise and those kind of things that 7 Tesla doesn't really help with anyway.
And so do I need to, as a broad question, do I need to do anything differently from, let's say, when I collect the data? Do I get layer-specific information by analyzing the same data differently? Do I need to set up the whole thing differently from the beginning? Yeah.
Yes, this is also getting already to the disadvantages of the field. Yes, there's a lot different. You need to acquire them differently. Specifically, there's one big problem and challenge in layer-dependent fMRI, aside of the fact that it's noisier as you go to smaller voxels. But the other thing is that with conventional fMRI methods like gradient echo bold, you are more sensitive to large draining veins. Like most of the oxygenation changes that we see with gradient echo bold happen to accumulate in the large, big vessels that are not closely aligned to the laminar neural structures. So one trick that I often do is to use a different fMRI contrast, which is called VASO, to be more locally specific to the blood volume change in the microvessels that are closely aligned with the laminar neural structures. So you use a different sequence, you use a different readout. Usually in the analysis, I think that's a big question also. There are more and more kind of streamlined layer-dependent fMRI analyses. Specifically, there's a software tool, Laney, that I'm writing with through Gulban that tries to help there. But overall, it's not like conventional fMRI. In conventional fMRI, it's really standardized. There's a conventional way of doing it, and you can run things like fsec prep, and it just works. In layer fMRI, that's not the case. You kind of need to fine-tune more, specifically also with respect to tissue segmentation. You need to have higher quality standards. Like in layer-dependent fMRI, we need to know kind of at which layer a given voxel centroid is located. And in order to estimate that, we need to have kind of geometrical models of the layers and given the cortical curvature. So to start with that, we need good tissue type segmentation. We need to know where the gray matter ends and where it starts between white matter and CSF. And there are a lot of automatic tools out there, good tools, FreeSurfer, Brain Voyager, and so on, that work quite well for conventional fMRI. In layer-dependent fMRI, often we need kind of higher quality standards. So very often you need to go manually in and correct things. And that's a problem. The first problem is that it's not really scalable. So if you just want to do it in your decision-making paradigm where you might have 60 participants, it's just a lot of work to go in there for every data set and manually correct it. So I think ultimately this will be solved with better analysis methods. Maybe machine learning is the solution. I don't know. The second big problem also is maybe a more conceptual difference compared to fMRI, where fMRI and neuroimaging, they had this reproducibility crisis. And I guess their solution to that is to use large N's and to use kind of user-independent analyses, which is different than other disciplines, like in kind of cellular neuroscience. When you put your electrode, you have the animal on your surgery table. You need to put the electrode in, listen to the neuron, pick a different one, and then until you find it. And there's a lot of manual skill. There's a trade to it. So in layer fMRI, we are kind of, as we are in the different spatial scales, we are kind of in the regime between standardized fMRI, kind of large scale, big data sets with standardized analysis compared to the manual labor of having a person on your surgery table. So in layer fMRI, there's a lot of optimization and manual work needed. Maybe to pick another metaphor here, that there's beer and wine, right? Beer is standardized. There are these multinational brands of beer corporation. You just pump it through Henry Ford assembly line production and it just works. And it always tastes the same and it's reproducible. And by reproducible, I mean homogeneous. You always get the same thing. In wine, there's no international brand of wine corporations, right? You need to tweak it a bit more, right? You need to consider which country you're from, if that season was very rainy, if you're getting your grapes from a North Hill or South side or whatever, and then you get the best wine by tweaking it on every case basis. And so layer fMRI is kind of more the wine of fMRI. You cannot simply run it through standardized pipelines, and sometimes we are kind of branded of saying that we are not doing the true science because it's more user dependent. But at the end, we get kind of consistently higher, reproducibly higher quality by doing that. So maybe that's one thing in layer dependent fMRI. Yes, you need to tweak your analysis, maybe even on a given individual person. You see that the motor cortex is folded in that person on that specific way. So you tweak it slightly different and optimize it different for that person. And then in the analysis, you see, oh, I have this artifact, so maybe I need to use this additional step, which is not kind of tweaking it, kind of so you can get any result that you want. It's just kind of a craft of getting the most high quality data, which is something fundamentally different that you would need to do both on the acquisition and analysis, which also requires kind of more skill and training, which is maybe one thing that's still holding us back. That Layer-fMRI is still hard, and kind of we are trying our best to kind of teach people how to use it on the scanner, online tutorials, click along, kind of example data sets on how to run the analysis, but it's more involved for sure.
Yeah, I mean, it's always going to be difficult to compete with an automated process that you can just, I mean, this is also obviously a problem that you can just click a couple of buttons and get your results. But I don't know, maybe you're going to get the more, the people who actually want to think more about what they do. Maybe.
It has its advantages, for sure. I mean, maybe another metaphor. Let's think of McDonald's burgers, right? They are very homogeneous. They're very reproducible. They always give you the same taste. But if you go to a gourmet chef, then he can kind of know that, okay, we are in fall now, so maybe the tomatoes are not as good, so maybe I use this different spice. And kind of to go to high quality stuff, you need to have more manual tweaking. It's not as scalable to that degree. Maybe also another aspect is for kind of discovery science, you cannot, like bold is not being invented by running standardized analyses, right? The big leaps in science are very often kind of not so hypothesis driven. We need to have this balance of exploring and then see what we see and then see how stable it is and so on. So sometimes I'm being called like when I this is not a vendetta,
what are
right?
you being called? What do they call you?
Let's say when I'm on the scanner and I say, okay, in this person I have a more artifact and I just can't get it better, so I'm changing my echo time and changing my temporal resolution slightly bit, and then this person has a thick motor cortex, I can do it perpendicular, so I'm optimizing everything for that person. That makes it...
Sorry, during data collection.
Exactly, in the data collection. So then I'm just trying to see what I see. I want to tweak the hell out of it. For my scanner, for my participant, where I know how it's folded, for my sequence, and for my analysis, I'm just seeing how much I can get out of it. And then I'm basically describing what I see. And some of my higher impact papers are coming from that. That basically, I'm just seeing what I see. And this is not really generalizable because it's really optimized for that person. And if I give those tools to another person, it might not work as well, right? However, it allows me to see things that nobody could see before. So I've been called, yeah, you're just on a fishing expedition, right? And then yes, I am, right? And I'm the fisherman with the smallest mesh size. I can catch fishes that nobody else can. And it's exciting. And then time will tell how reproducible it is. And it's this kind of double-sided sword. So I have this advantage of not being automatized. So I'm in this unique seat to see something and to discover stuff, right? And then at the same time, one reason why we are privileged in method development is that we always can kind of switch gears between the visionary researcher towards the janitor, like the scanner janitor, the enabler, right? Where it's really important that you not only show the highest resolution image where you see a new feature and you describe it, like the mirrored fingers or sampling layers or something that makes it to higher impact application, but then we also need to do the dirty work of kind of making those tools robust, making them available, writing manuals, doing tutorials, doing the teaching so everybody else can use it. And that's not really rewarded in the kind of scientific hiring procedures and so on. However, it's also nice to have this kind of support role often as a technical person that it's easier to find jobs, for example. You don't need to compete for grants as much because there are always kind of these support jobs as well. Yeah, okay. So it's nice to so
if I understand your metaphors correctly, you are both a high-end gourmet chef and you also clean your toilets. Is that roughly the...
Exactly, yes. I think I'm, to some degree, I need to be the garbage man. It's a kind of useful job for the community. Imagine there's no garbage man, but it's a kind of a fine balance to live in both worlds. And I'm a star scientist here, and so it's hard to bridge the gap. Yes, sorry.
Yeah, no, I mean, I think this is a really interesting kind of topic or question because as you said, the breakthroughs don't happen by just, running the thing that everyone's running with the same, you're not going to have a breakthrough study by using, I don't know, psychology questionnaires that someone else developed and then another questionnaire, and then you correlate the two with a standard, like that's not really going to lead to anything particularly insightful probably. So I completely understand what you're trying to say with the trying to tweak it, but at the same time, I mean, how do you manage to make it reproducible? Is it just doing it with lots and lots of people, and do you try and separate the exploration from the, basically, how do you separate the exploration from the confirmation in this context? If a lot of the work involves so much of you actually looking at what you're doing, and yeah.
Like, I'm not sure if I have a solution. It's just kind of a lot of work. Like you do something, you do it again, and then, like, if you see something new, then you just invite the same person and do it again, retest, and see how stable those patterns are. I think there's a lot of non-science work in making it kind of usable, kind of the janitor work of the scanner. Like, you need to work with the vendors, and to work with them is kind of difficult. They care about different things, and also kind of the knowledge on knowing how the scanner works internally is not research. You don't learn about this in academic journals, right? It's kind of inside knowledge and depends on kind of industrial decisions that the vendors made commercially. And still, you need to keep up with that a lot. And that it's not kind of open. They need to build your kind of networks with people from the vendors and so on. Ultimately, they have something like an app store for sequences where I can kind of upload my sequence. And now the Layer-fMRI Bastos sequence that I'm providing is installed in like more than half of the 7 Tesla scanners out there, certainly more than 50 or so. So, and then people do it again, and then it's iterative, right? You're bombarded with a lot of questions. If I get the same question 3 times, I put it on the blog, which then I have a huge FAQ for how to do that. And same for analysis. Like, it's a lot of effort to kind of do like screen recordings, click through your example data set, teach people how to do it. And then it slowly gets reproducible, and other people do the same thing and see the same features across layers. And usually time will tell. And yeah, it's a hard balance. And maybe it's something for the kind of closing questions that you usually have in your podcast, where you ask what people wish that they would have learned like earlier. And I think that balance is something I haven't really learned yet. And I wish I would have learned earlier to think more big picture, like in the sense that sometimes I feel I'm investing years and years for building a software for other people to use, because they're very thankful for it and use it and they get citations, but it doesn't allows me to be seen as a kind of innovative researcher myself. I'm more judged as an enabler or kind of a service person in grant reviews or something, if I just provide software, because the incentive structure just doesn't work like that. And we as scientists, we have an incredible luxury that we can kind of, we get government funding, grant funding, taxpayers' money usually, and we can pick the projects that kind of fit us, what I like to do right now, what I find fun, what fits my skill set. And if it doesn't work out, like in science, some things doesn't work out, right? We are even encouraged to do risks. And sometimes I wish I would have learned sooner to kind of to think big picture early on, to not only be the janitor, but sometimes kind of to explore more and rather kind of push the field and show them where there's interesting information to harvest to some degree. So I think very often the scientific industry is frustrating. It's brutal out there, right? You need to cope with rejections from grants. You need to cope with kind of hateful, unnecessary, destructive reviews. And so very often that's in our kind of mind, like my emotions are kind of tuned to a way that I want to do studies that are kind of easy to do and that I can defend in front of a reviewer, which is not the right approach, I think. So to answer your question on how you balance, like sometimes I pick projects that are kind of useful for the community. They're easy to do, write a software that helps everybody, be the garbage man, and kind of forgetting kind of the big picture question, where I actually want to end up in 10 years, how I have the biggest impact for the field. So at the end, I think I just need to do both in my discipline. And we shouldn't be guided by kind of the frustration of mental energy being put in kind of the low-hanging fruits and easy projects, which are sometimes kind of the janitor works, to be useful to people in your institution or something. We need to kind of have our own questions too on the side, or do the garbage work on the side. We need to do both.
Yeah. It's a fun thing, right? If it kind of works out, then in 10 years, people will just be running this routinely, and you'll be sitting there going like, you have no idea how much work I put into making this easy to use. people won't even know that they'd have to be grateful for it. I guess the same way that now you can just use all these fMRI, the standard things, and if you have a kind of new paradigm, a new task, then you're not even aware of like how much work went into making it so that you can do it fairly easily. So for Layer-fMRI and you in general, what are kind of some plans? I mean, what do you think is going to happen? I guess resolution is going to get higher in the coming years. But yeah, I'm just curious, kind of what do you think? I mean, maybe two things. One, kind of what are some fairly obvious things that you think are probably going to happen in the next couple of years? And then secondly, also, what is something you'd really like to see, but you're like, well, I'm not sure maybe some of the things you'd really like to see will happen, but yeah, basically what will happen and what would you like to happen?
Like resolution is going to get better. It will have kind of compromises. You will be slower. Hardware is going to be better. There's this renaissance of new hardware. Like we had multi-channel RF coils since 20 years. We had 7 Tesla since 20 years. And there was little development. Now with the new gradients and with the higher field strength beyond 7 Tesla, there's a new push. So things just will be the resolution will grow. Clearly, the Layer-fMRI will be easier simply because it has to. There are more and more people using it, which means there's a lot of mental energy from all different labs with all different expertise, and there's no way around that. It will just be easier. One very obvious thing that I'm actively working on is kind of whole brain Layer-fMRI that's kind of robust. There are a few people trying to get towards kind of whole brain. Usually, most people still focus on a given brain area and then look at the different layer connection, feed forward, feedback, input, output, and so on, which is kind of ironic that Layer-fMRI is inherently a connectivity tool, and you don't really always see kind of if there's output, where this output is going to, or if there's input, where this input is coming from. So ultimately, Layer-fMRI really will fully develop its promise if we have whole brain. And to have 200 slices at TRs that neuroscientists like of very few seconds only, maybe 3, that's still hard. And so I think in the next few years, maybe 4 years, we have a nice connectome, whole brain functional connectivity across the layers as a kind of baseline data sets available. I think that's something that I'm working on and that is just going to happen. Other things, like I can extrapolate a bit from the changes that I currently see on my blog, layerfmri.com/papers. I track all the papers out there and then some trends. So in the early days, it was really kind of acquisition, hardware focused. Then there was this golden age of understanding the contrast, a lot of stuff in animal models. Then it moved towards kind of more acquisition methods, sequences, and until kind of the neuroscientists really jumped on. And since then, it's exponentially growing. So I think the field will shift more away from people like me, methods developers, more to application-focused people, which sometimes I see kind of weird quality papers out there. So I hope we're going to do it right. And this shift towards applications. And these applications are moving away from the early sensory areas, motor, visual, auditory, to more kind of higher cognitive areas like the DLPFC or more network kind of ideas. Hippocampus, I think, is just a thing that's going to happen. Where we are also kind of working on it right now with Khazar Ahmadi, visiting from Bochum, looking at kind of memory. So the kind of inevitable change will be kind of to apply it on the conventional tasks that people do in cognitive neuroimaging, maybe decision making. We'll just do the same old task with now layer-dependent fMRI. Other things where I'm still frustrated that it hasn't really happened is kind of more clinical applications, because there are maybe a handful of review papers that talk about the promise of layer-dependent fMRI for neurodegenerative diseases where specific motor neurons are affected in a motor system that are degenerated. And then you can look at that with layer-dependent fMRI. It's psychosis, schizophrenia, also Alzheimer's with respect to the different layers in the entorhinal cortex. There are a few studies that kind of going there, but it's still hard. We did some study here at NIH with focal hand dystonia patient, which was a huge learning curve to work with patients, and they move and they have different needs and they're not as trained. And still it was like not as hard as I expected, I guess, to look at focal hand dystonia, which are patients. It's a quite common neurological disorder where people kind of use their fingers in everyday life, but for some tasks they just cramp, like writer's cramp or musician's cramp. And then there are hypotheses about that with respect to microcircuitry, namely that it's a lack of surround inhibition of the individual finger, which seems to be what we are seeing as well. So I think more clinical applications will come in. As more cognitive neuroscientists will use it, it will be more scalable. There will be larger N's and those kind of things. And then I'm not really sure how we will merge in with the neuroimaging community of kind of user-independent, large and scalable data sets where you're not allowed to touch the data. And so there will be something where I hope that the needs of layer-dependent fMRI will be met somehow, to have remaining flexibility in acquisition and analysis without being branded as being on a fishing expedition or something like that. And then I guess I see a bit of the open science movement in layer-dependent fMRI. Since 2019, I think the more and more people at least share the data, because in the field of method development, people are really protective of their intellectual properties, because maybe the closeness with the vendors and they want to have patents and become rich if they develop their sequence. It's not standard that you share your data. And still, for code sharing of scanner programming code, there's nothing, because the vendors, they don't want you to, right? You need to sign something that if you want to develop something with a vendor, that you're not going to post that code. And there are kind of new developments that I hope are happening. So hopefully the biggest thing that I want to see is that it's getting easier, specifically also with respect to acquisition methods like blood volume sensitive methods that are not kind of the standard bold methods that are mostly sensitive to large draining veins in there. And maybe the biggest challenge in the near future will be that Layer-fMRI is still a method of opportunity, a method with potential. It hasn't really lost its innocence yet, that it needs to be useful. It needs to give grant money and fund scanners and so on. So as soon as it's really established, I think then people want to use it and have it turnkey. So I think there will be a lot of criticism and kind of pointing fingers. Oh, what's this artifact? I can work with a method that sometimes works and I have a dropout rate of 10% or something. Right now, we are still in that domain that I don't care if I have a dropout rate of 10%. And if there's too much motion, which sometimes happens, it's a problem more for layer-dependent fMRI, and I can just ignore it so far. But at some point, I will not be able to, because then people will complain and say, well, I have my patient flown in now. This needs to work, and we are not at that kind of robust level just yet.
Yeah, I guess hypothetical example, but if you had someone with psychosis and you, I don't know, wanted to test whether it was this or that kind of psychosis and that could be done with it, I guess if there's no alternative, maybe they'll still try. That might not work, but okay, so it's a lot of streamlining, seems to me, right? Like a lot of taking a thing that already exists in some contexts and just like making it work more easily, more, like, as I said, like with fewer errors or problems or whatever. Okay. Yeah, so at the end of each interview, I asked my guests the same 3 questions. I guess one of them we've kind of already answered. But to start with the first one, what's a book or paper you think what people should read? Can be old, new, famous, unknown. Yeah, just some sort of reading recommendation.
Yeah, it depends. There are a lot of papers, as I said on the blog. All 260 are listed there. I gave a recent 48.
Sorry, just as people usually often recommend more than one, but I'm going to limit it to less than 250.
So there are a lot of metrics on the website where I'm kind of summarizing the most cited paper, maybe good papers for people that want to start in the field. And recently, for an educational workshop, we asked all the faculty of all the Layer-fMRI leaders in the field what they recommend. And I think one of the introductory papers for acquisition methods, not so much brain focus, but for acquisition and the scanners, and I guess the first half of this podcast, there's a paper from Saskia Bollmann in the Progress in Neurobiology journal 2020, which is called New Acquisition Techniques and Their Prospects for the Achievable Resolution in fMRI. And I think that's really written for the lay audience without too many kind of specific terms. The most cited paper is one from Jonathan Polimeni with the title Laminar Analysis of 7 Tesla Bold Using an Imposed Spatial Activation Pattern in Human V1, which is kind of old. It's from 2010, and it's just kind of lifting the curtain of kind of what Layer-fMRI could do. It basically showed that you can do it, and there's signal, but it didn't really tell you a lot on kind of the entire landscape that would evolve in the decades to come. I think that there's a YouTube channel, Layer-fMRI, which has a lot of kind of the overarching kind of keynote lectures of people that kind of give an good overview of fMRI. Actually, one from Peter Bandettini that I would recommend. that I found kind of inspiring also for finding new questions in layer-dependent fMRI. But I think there's not a real one paper that I think everybody would read. The book that I almost give every student that I found that it was very inspiring for me was Surely You Are Choking, Mr. Feynman, that made me study physics. And it's just about the joy of finding things out, about scientific integrity. And it's kind of entertaining. It's still now, when sometimes I'm dealing with rejections, I read it and remember kind of that I'm in the field where I want to be, even though it's kind of old and outdated. And he has some controversial opinions about kind of gender questions where he might have been progressive in those days, but it's really outdated nowadays. But there's a lot of cool stuff in there that makes you thrive for science.
Okay, yeah, it's funny. It's funny. I had a very brief period in which I wanted to be a physicist. Basically, I wanted to do music for most of my life, and then at some point I was like, actually, I don't know whether I actually want to do that as a job. And anyway, so I randomly, in a bookstore, came across that book by Feynman, obviously in the slightly more awkward phrasing in the German translation. Sie blieben wohl zu scherzen, which is just a terrible way of putting it. But yeah, no, I was like, oh, this is so cool. This is what I want to do. And then I just had the worst physics teachers next year. And then that was kind of the end of that. And since then, I've never been interested in physics again. But yeah, haven't read it since then, though. So yeah, no idea. But yeah, I guess it seems to be a book that gets people into physics. Yeah, something you wish you'd learned sooner. Do you want to expand on something said earlier, or should I just link back to it? Or
no, I think like the balance of being the janitor and the visionary scientist is something I wish I would have learned a bit sooner. I'm still kind of circling back and forth. One aspect that I definitely wish I would have learned sooner is kind of how many skills it involves to be a kind of a scientist in general, a researcher. Like I studied physics because it's contained, you have your ground truth. And actually I failed English in school, right? I dropped out for a year and I was very bad at reading and writing. And so I did physics because I didn't need English and I didn't need reading and writing. And it's ironic that now I spend most of my day reading and writing English. So something that I wish I would have learned sooner is that kind of as a scientist, you cannot have this attitude that, well, I'm focusing on the science, I'm not publishing. You at the end need to learn how to advertise yourself, how to build your brand and those kind of things, specifically for incoming postdocs. I think that's something you will need to rely on. And maybe it's awkward. And I did physics because I can be in the basement, socially awkward and do my stuff and do it well. But at the end, you need to learn to be a communicator, and you need to learn that science is done by people. There might be a ground truth down there, but you need to advertise it, and you need to invest in this skill. And like in the first 3 years of my PhD, I didn't publish. I didn't see the point, despite people recommending it me, because I built my sequences, people used it, and that was my reward, right? I saw that I was useful to the community, but at the end, publishing is just something you need to do. It's like paying your taxes. Even though you have other plans in your life and your long term, you just publish, and you publish whatever, and it's just something you do. And then kind of there's all different aspects in being a researcher, and there's no way around it. That's something I recommend people kind of not neglect. And it's something I wish I would have learned sooner. And I'm saying this also because I see it in other people that say, I get my talks at conferences, I get my recognitions, I don't need to publish this, do I? No, you do. And you need to kind of build your network and to have the future boss. And you probably know your future boss already. So be kind to people and be a people person, even though it's not your strength. And maybe that's even the reason why you went into a nerd field.
So I'm just trying to imagine that conversation between you and your supervisor, and saying, you should publish this. And you just say, like, but why? Because that's how the system works. Yeah. I guess, well, I was going to, final question is advice for PhD students, postdocs, or people in that kind of roughly that area. Is it kind of linked to what you just said, or do you have some completely other advice?
No, I think it's that you need to build your things. Yeah. Maybe one thing I also learned, and maybe I'm overdoing it, is to accept that you cannot be perfect, especially for PhD theses. You can write your thesis for the rest of your life. At some point, you just need to make a cut and say, this is it. And you can always kind of optimize it further and further. And maybe I'm a very bad writer, and I just accepted it. And if you read my blog, it's full of spelling mistakes and whatever. And I'm fine with it. And if in my papers, sometimes there are things that are kind of weird and I don't really have a perfect answer, I still make it into a paper and I acknowledge that this is unsure and I don't know. But ultimately, I think, that the acknowledgement not to be perfect or mind the gap or whatever, like the UK Metro says, is fine. Acknowledge that you have this gap. And that's something I learned and maybe overdoing it right now. But that's something I would recommend because that's something I think that people are literally self-sabotaging themselves, that they are trying to be perfect. And there's still this question, I'm not sure about this. It's fine. As long as you're transparent, it's okay not to be perfect.
Yeah, it's funny. I remember when I started my PhD, I wanted to really have my thesis be like this thing. And then as I was going through my PhD, when I started writing, I was like, oh, this just doesn't matter. Because I guess the metric we're counted by is papers and these kind of things. And so I was like, yeah, genuinely no one's going to, it has to be like a certain standard, obviously, so I don't fail. And so I get like a decent grade for this. But I think actually one thing that's quite nice for us also is that, and I'm assuming it's similar in the field you worked in, is that the thesis in itself, there's very little you can actually do. Unless you actually make it basically into, because the unit of measurement in a way is a paper, right? And through your PhD, you kind of made those. And sure, there's some unpublished stuff and whatever, but at the end of the day, this isn't, I don't know what it's like in other fields, but I imagine maybe if in the humanities or whatever, then that's the writing of the thesis itself can be a lot more of a thing. But then it seemed to me that someone's like, oh, this is I've done the work. Now it's just summarizing it basically for people to understand.
I struggled with kind of how much you include, right? You always have this other experiment that didn't make it to a paper. Do you include it now? And how do you packet it? Actually, I would like to acquire a few more people. And then I also have this other open issue solved. But at some point you need to but it's just something you do. And along those lines, as I said, it's more and more important to kind of build your friends, build your networks, because at the end, science is brutal and frustrating, especially in the science industry, how it works. So surround yourself with nice people that you like, because science is done by people.
Okay, well, that's a nice final word. So thank you very much. And we managed to do this. The audience doesn't know this, so I mentioned now. Without the drilling starting again in your building, we managed to get through the entire episode, apart from the first 5 minutes or whatever. Don't know whether that'll be audible, but we made it.
Yeah, thanks for having me. And I really like your podcast. It's a nice service that you do for the community. And congratulations on kind of more than 100 episodes already. It's really a lot of work, and I appreciate it. Thanks.
Thank you.